All right. Good morning, everyone. We've spent the last week reviewing chapter one, and so this week is going to be a review of chapter two. I'm going to try and keep it brief, in the interest of just brevity, because we're also like we have a review of chapter one and two online already, which is done by some of the students who were already going through this stuff. So the key here is you guiding me to explain some topics more and other topics less. So feel free to unmute. I particularly encourage, if you can, keep your video on. It's more interactive. But no pressure that way. So let me get started with chapter two. Um, right. Okay. So far we've spoken about linear regression in a univariate case where you have a random variable x and you're predicting a random variable y. Now we're moving to the multivariate case where x is, say, you have a matrix x which has multiple columns, and that's one way to think about it. And then you want to predict y from this x. So before like getting into like how we do that, there are some key takeaways as to why linear regression matters. Obviously, the first thing is it's very straightforward. You have a column of predictors, you have a column of responses, you want to fit your column of predictors to the responses. Um, and that's about it. The other point is that it is a simple foundation, so you can play around with multiple linear regressions, multiple different techniques, so on and so forth. Um, it's a standard method, so people use it to communicate. So regression is not just a statistical tool. It also has its origins in the econometrics literature. It has its origins in physical experiment science. So a bunch of different fields converged on linear regression as like one of the foundational techniques, which is why it works even today. So it's like very unique for a tool to have so much applicability over so many years. So yeah, standard method, but a lot of people tend to confuse the relationships that you discover in a regression analysis with causality. So a lot of people you will see on occasion, they tend to confuse x has a relationship with y as x causes y, and that is a fallacy that you have to do some more testing before you can make that claim. And people don't, so they just make the claim, and that is wrong, which is where you find the origin of the statement correlation is not causation. So just keep that in mind when you're doing linear regression. It's not the only way, the only thing you need to do in order to test causality, right? So getting back to the setup we discussed, where numerical variable y and x is a p-dimensional vector of predictor variables. um, we've seen that the mean squared optimal predictor is the conditional expectation in the last chapter. If anyone is unclear with expectations and variances, we should pause now. So I'll hold off for a minute and you can tell me.
Hi, if you can go through the expectation bit again, that would be great.
Mhm.
Thank you.
So think about think about this as you have a bunch of data, and oh boy, this is the wrong style of pencil. Uniform. This is why I hate not having the iPad. Yay, I got the iPad. Okay, give me 1 minute. Where are we? Okay, so now consider this setup where, okay, you have some data, you have another set of data, and you want to say tell someone about your data. And how can you go about telling someone about your data set? Can you tell them I have 1, 3, 5, 6, 9, and I have 1, 2, 4, 8, 10, 12, 11, 19? Like, how do you describe data? This is open to everyone. Like, how do you describe data sets?
Like, for example, you do summary statistic, like you take a mean
Hmm.
and you can say, okay, or you can take variance or standard deviation, so you can say how spread apart the data is.
Wait, so you know mean and variances?
I know mean and variance, but I don't get it. Like why you use the term expectation?
I see. So the mean is, in a sense, the central value of a distribution, right?
Yeah,
Um,
yeah,
the median is similar, but there are subtle differences. But I would say the mean is the average, right?
yes,
So in a sense, it summarizes where your distribution lies around, right?
yes, yeah, that's right.
And that is, in just plain English, it is the expected value you will get from that distribution. So if
Oh,
you draw a lot of samples from a distribution, if there is this sort of distribution and you're drawing a bunch of samples from this distribution, you will get points that fall on this line, but most likely it will be around where the distribution is peaked, right? If this is a probability distribution, the probability of getting these points is much higher than the probability of getting these points, correct?
yes, that's right.
So this will be around somewhere here, will be the expected value of some distribution, of this distribution. That's what that in a that's in plain English and like simple words, that's what the expectation is trying to tell you, that this is the expected value.
So it's basically mean.
It's the
Is it?
mean, yeah.
But then why not use the word mean? Why use the
So
expectation?
an expectation is a more general, I guess. So there are different terms that we use. So mean is also the first moment, variance is also the second moment, and there are like any number of moments for a distribution. Um, with the idea that okay, if these two distributions have the same mean, but they are like individually, you can see that they are different distributions, right?
Right. Yeah.
So then I can't just use the mean to describe it, because then there is no difference between the two, right? So I need
Yeah.
something more. So they came up with this idea of second moment or variance. And then when mean is the same, variance is the same, but the distributions are still individually different, you can construct those things, right?
Yeah.
How do
That's
you
right.
describe it? And you need a third moment, which is called the skew. And there's the fourth moment, which is called the kurtosis. And like you can define n number of moments. And that sort of motivates the idea that you need something better to compare distributions. You can't just keep going moment after moment after moment all the time. But that's not in this chapter. That's just in general.
So
So yeah.
okay, go on. Sorry, carry on.
Okay. So the expectation is basically just another way of saying the mean. The expectation of the second, I don't know if you can call this the expectation of the second moment, or is it should be just the second moment, but expectation of x minus the mean, the whole square. This is called the variance. Like the variance is defined like this.
But that's different from what we study in statistic, isn't it? In statistic, we subtract, like, yeah, I understand, we subtract each data point from the mean, and then we take a square of it, and then we do the like sum through everything. So did you
Correct.
mean?
And there you're making this assumption that each point was drawn with a particular probability, right?
Making an assumption of.
So when you have some samples, right, the way you describe this is there is some data generating process, and I'm drawing these samples from that process.
Yes,
Any
yeah.
any data set,
Yeah, that's right.
right? You want to find the function that produced that data,
Define. Yes, that's right.
right?
Yeah.
And so there is always this red line, this probability distribution over the data set. Every data set has a distribution. Would you agree?
Yes, yeah,
It can have a distribution that's simple, that's complicated, that's but it has a distribution.
yeah.
That
And
is the fundamental assumption we make, because if there is no structure, then we can't find anything.
yes,
Mhm.
yeah, that makes sense. And the distribution can be either discrete or continuous, depending
It can
on.
be either discrete or continuous. So this is how we denote discrete distribution. This line and then a circle at the point.
Yeah, got
We
it.
don't have this thing then, right?
Yeah,
But
yeah,
it has a distribution. And
yeah,
if it has a distribution, it has some summary statistics.
yeah,
It has some expected value. And as you described in English, so you subtract the data point x from the mean
yeah.
and you square it. And then you sum over all of xi. This is typically how you do it, right?
Yes, yes, that's right. Yeah,
And then you take 1 by
yes, yeah,
n minus 1 and n, but I'm not going to that difference right now. Um, right? This is how you describe variance.
yes, yeah, that's
Now,
right.
what you're implicitly doing is this idea of Monte Carlo, which is saying that instead of when I have this sort of distribution and I have some samples from this distribution, I'm going to, instead of when I don't know the probability of this point, um, in the true distribution, I'm just going to take the probability of that point in the data, right?
Right.
When you're summing over these xi's, there are some xi's occur more than others. Is this true?
What do you mean by some xi occurs more than other?
Right. So in
Isn't
this
that
data
these are
set,
data points?
so if you have data points x4, x5, x6 out here, in
Yeah,
their vicinity, you will have less samples than x1, x2, x3. Is this fair?
I will have less sample there.
Sorry, you will have less samples in the vicinity of this compared to this, because the probability of sampling this is more.
Ah, right, because the probability is higher, so I would be
Yep.
doing more sampling from higher probability distribution.
So the technically correct way is saying you will be sampling and you will end up with more values from this region,
Yes, yeah,
right?
right, yeah,
And so by taking this average and giving each sample equal weight, you are saying, okay, I mean, these are going to be more than these,
right, okay,
correct? So
yeah,
there was this dude, like um there is some very simple theory behind this, which says that if you want to figure out what the probability of stuff happening in an experiment is, just keep performing the experiment again and again.
right, yeah.
I don't know why my video froze, but it's frozen. Oh man, don't die on me. Okay, cool. Okay. Anyway, so that was some motivation. So in a sense, you are just taking the expectation um, by using the samples as opposed to the true values. What's going?
So
All
you
right.
replace the whole sigma thing and then the
Right.
divide by
So
n with e.
the sigma thing. So the idea behind Monte Carlo sampling is if you have an experiment and you don't know what the true distribution is that describes the data that is generated from it, then you just keep repeating the experiment. If you want to figure out, for example, if you have a coin that is biased, bias means it's more likely to turn up one side than the other, right?
Mhm.
A fake, like a cheater's coin.
Yeah.
Then how do you figure out which side is more likely to turn up?
You don't know.
Just flip it
So
1500 times. You will definitely start to see a pattern.
right. Okay.
Mhm.
Yeah.
Same with, so this idea came from this guy who wanted to analyze playing solitaire. And he was like, I wonder what are the starting combinations that make me more likely to win than others. And he just played a bunch of games with some starting combinations that he wanted to analyze. The math is really complicated there because there are 52 cards, they can show up in a certain sequence, so on and so forth, right?
Yeah.
But if you just play the experiment, you can get an estimate of how likely you are to finish from certain combinations compared to others.
Yeah. Makes sense.
So that's this idea of summation over I xi. That's what you're doing. Xi minus expectation of x. This part is just centering. So you're calculating the distance from the center. But the Monte Carlo stuff is this, like taking a summation over I and just doing 1 by n, like giving each point equal weight.
Right. Okay.
Okay, fair
Yeah.
enough. So that's, yeah, the idea of expectation comes in different ways. Like you already been working with expectation in many places without realizing it.
Like.
Like calculating your variance is basically like taking an expectation. This is the formula for variance, and you're approximating the same thing. So this is the true variance, but we just have data, right? We don't have the entire function. So we have sample variance, and we use sample variance as an estimate of true variance. Is this clear?
Yeah.
So anywhere where you're working with data, you're creating estimates because you do not know what lies between the data, right? You don't know if the function could be something like this, right? It very well could be. It passes through all of the data points, but it's just a very weird function. So we're interpolating between the data, saying this is the smoothest way to do this. So we're going to assume that this simple model works.
Yeah.
And that's how you do a lot of statistics. You just assume that, that the simplest possible model is the best explanation, or the one with least assumptions is the best explanation.
Right. Yeah.
Mhm.
Yeah. Makes
So that's
sense.
your
Yes.
expectation. Mean variance describing distributions. We discussed in the last chapter that the mean squared optimal predictor is the conditional expectation, which is, and again, to remind you, this could be a function. It's not like a constant value, because like so far we spoke of expectation as like this fixed value, the center of the distribution, but now this is conditional expectation. Y given x. Oops. Okay. Anyway, um, so the idea is that, in a very, in the simplest possible way, if you have multiple columns for x and you want to predict a y, then the simplest thing you can do is fit each individual column and obtain its coefficient to describe y. And in a sense, that is what we are doing. So if you solve the formula that we solved in the first chapter, um where do we go? So in the first chapter we got this formula, which said that the parameter is equal to covariance of xy upon variance of x, and this v inverse is this variance of x. We got this formula, and now we can, because we have x and y, we can actually calculate this. And when you can calculate something with the data by hand, it's called having a closed form solution, By hand, I don't mean like literally on paper, but like using a computer and stuff, where you don't have to do stochastic stuff. You know that there is a deterministic answer, like no matter what I do, I will arrive at this same answer. That's called a closed form solution. So basically you have an equation for the answer and you have to plug in values and solve for it. um, and the key point here is like it's not very different jumping from a single variable x to like a column of multiple columns of variables x, I, x, j, whatever. It's not that big a deal. However, one thing you have to remember is you are making some sort of assumptions. um, Not making some sort of assumptions, but the structure of this, actually I'll get to that after a point. Let me first talk about one of the key assumptions you are making. Also, I sort of solved for it on the side, like when I say mean squared optimal predictor, what it means, all of that. Based on our first chapter, I gave you a nice sort of explanation on why it is a minima, why this expectation of y given x, in case you don't remember from the first chapter. But you can go through that on your own time. Right now, the reason, like the first assumption we make when we throw linear regression at a model is that a linear model is a good approximation to the true model. And that is important because, again, we saw in the first chapter there were these three models. There's a plot where we fix a very complicated model that belongs to the true family. So if the true model is something of a sine curve, then I start with this curve and I want to get to this curve. But because I don't have enough data, I actually end up with this curve. And what he's saying is, if you have this blue curve versus if you have this linear model, the linear model actually works better. So it's a more reasonable approximation, even though the blue curve belongs to the true family of sine curves. So in a lot of cases, it makes sense to just throw a linear model at it, make the simplest possible assumption. And because of this idea of smoothness, where we say that it's not varying like mad between the points, like this one, because of the smoothness idea, we can actually take a point and Taylor expand about it. So Taylor expansion just uses derivatives to like build this region around a point where you can say, okay, the function goes like this, something like that, right? So that's the motivation behind Taylor expansion, is that a point, that the function around a point will not vary like crazy. So smoothness assumptions, if you can make that smoothness assumption, you can Taylor expand and get this equation describing the function in a very limited region, say delta, about a point x. And that is what these two lines are about. So yeah, you should definitely read up on Taylor expansion. I've also provided some notes describing what is going on. I should leave that in actually. Okay. Now, moving on from that. Um, Hold on. Yep. All right. Thank you. Um, so in the last chapter, we saw this B inverse covariance of XY. Also, stop me if I'm going too fast. Stop me if I'm going too slow. Yeah, just keep giving me feedback on what you know, what you don't know. Ask me questions at any point, even if they're really simple questions. I'm pretty sure everyone will benefit from it. Um, yeah, we spoke about multiple regression could just be simple linear regression for each regressor and then adding them up. One important thing is correlation. So correlation is this idea of one column having nothing to do with the other column. So if you have 1, 2, 3, you do not want a 2, 4, 6 column here, because then this column is a linear product of the other one. So xi, 2xi then becomes equal to this column xj, correct? So you don't want that to happen because they're not giving you any extra information about the data. This has the same pattern as this one, essentially. And that is the idea, that you don't want the same pattern to be exhibited twice in the data set, such that one can
Um,
explain the other.
Hello, Swapnil. This is co-linearity or correlation related to?
This is collinearity. I was getting to correlation from the perspective that, two columns should not be correlated with each other in the sense like they exhibit the same pattern.
Okay, okay.
So yeah, but thank you for that point. And so 2 points about that. Because of this, we inverse. Where did we go? There was a footnote here. Okay, that's what I was going for. So this footnote explains it much better. Such So v, the variance of x, can be broken up into v half times v half. And when you multiply this result, I thought this was here, but maybe it's further on ahead. Or maybe it's just in the footnotes, and I was reading that for a while. Yeah, it's just in the footnotes. So the point they're trying to get at is, if there is no correlation, then this will be a diagonal vector. So if one column is uncorrelated with the other, then so this is how you build this is how you build a covariance matrix. I'm not going to get into this right now, but you should definitely look up the difference between correlation and covariance. It's a little subtle,
Isn't that
but
correlation is just a standardized version of covariance?
this
Because
is true.
because
This
in
is true, but
covariance,
you
you
need to know what covariance is for that.
yeah, but in covariance, isn't that you just where covariance, like you calculate that between two features to see how far apart they are, like, or how they are related to each other.
How they vary with each other. Yep.
Yeah, that's right. Yeah.
Yep, that's essentially it. But there is this mathematical formula that you should be familiar with, and that's why I mentioned that you should look that up, because I'm not covering it right now. But this idea of covariance matrix is so if you have xi or let's say x1, x2, x3, and so on, then your covariance matrix is, you obtain this. And again, I'm going to be abusing notation here, but essentially what you're doing is 1 by n x transpose x for your sample covariance matrix. um and yeah so you can imagine this is x1 times x1, um or to put it better, covariance of x1 and x1, which is equivalent to the variance of x1. Here you have covariance of x1 and x2. Covariance is a symmetric operator, so covariance of x1 and x2 is equal to x2 and x1. So you can think of it as, if x varies with y, I'm just taking a regular x and y here. This has nothing to do with your data set x and your predictor y. I just Okay. If u varies with u, if u vector varies with v vector, then this is the same thing as vector varying with u vector. Like they're going to vary the same way if they vary together. And that is this idea of why covariance is symmetric. But you can also solve for it and you'll obtain the same answer. Um, if I'm getting into all that, I might as well just tell you the formula for covariance. It's the expected value of u minus expectation of u times v minus the expectation of v. So how far is v varying from v's mean? How far is u varying from u's mean? And then take both of these together. Remember that in variance you were doing u minus expectation of u times u minus expectation of u. So in a sense, how u varies with itself. And that is why this covariance of x1 times x1 is equal to variance of x1. So if you substitute u here, you'll just obtain variance. If you substitute u here. So yeah, I basically explained that. And correlation, as Vishy put it, as standardized variance. Now, what we are saying is, if there is no correlation, if u does not vary with v, there is no relationship. And by varying together, I mean if u goes up, v goes up. That sort of thing. Again, this is very hand wavy, and you should look up exactly what correlation means. But the idea is there is this term goes to zero as this data gets uncorrelated, and that is what you want. So as you get uncorrelated columns that tell you different things about the data, they may not be like the same level of information. Some columns may not actually tell you anything about the data, but at least they're not redundant columns. That's the point. So you shouldn't have redundant columns in your matrix. That is the entire point of uncorrelation. Because if you do, then your matrix becomes a low rank matrix. There are some issues with the rank of the matrix, and for those with knowledge of linear algebra, you will understand that the inverse then is not easy to find or does not exist in a lot of cases, and so on and so forth. But so it causes downstream issues. But anyway, the point is you want uncorrelated data sets, otherwise linear regression runs into issues. What issues come up, we will examine later. Okay, so I spent a lot of time on that. Yeah, this idea of collinearity is exactly what Kushal said. 1 2 3 2 4 6, they essentially lie on the same line. So if you have um, points 1 2 3, 2 points always lie on the same line. So what am I trying to say here? um, in terms of vectors, um, it's too complicated. All I'm trying to say is, if one vector is a linear combination of the other vectors, then it's a problem. That's literally it. So if you yeah, if a matrix is a transformation, I don't want to get into that, but yeah, I'll leave you with this much for now. This happens if one of the predictors are linearly dependent on each other, and one is a linear combination of the other. So this could be a linear combination of two other columns, but yeah, you get the idea. Okay, moving on. I spent a lot of time discussing V has exactly one eigenvalue, which is 0. I'm not going to do that at all this time because that took like 20 minutes the last time, and it's probably recorded. Okay, what else do I want to say? So some ways of dealing with collinearity: just drop the column, get new data, or try to appeal to some extra principle. And this extra principle idea is something to do with regularization. When you optimize using something other than just your optimization of objective function, that is this idea of regularizing your optimizer. Yeah, I don't think I want to say more about that. Okay, now this important idea, the prediction and its error. So you have a point y somewhere here. You make a prediction for the same x. So you say your predicted y hat is somewhere here. This is your true y. Should change color. And so there is this leftover error at this x that we call the residual. And the idea is that this residual can tell us a lot about how our predictions are doing. So, for example, if the residual is a lot, then clearly you're not doing very well. The residual is very small, you're doing very well. But it's not as simple as that. A lot of times, you might make certain assumptions about the data set, which you can test using these residuals. And there's a lot of very cool math that uses residuals entirely for analysis. But of course, that's separate from everything we're doing here. So what they analyze in the chapter is this, not chapter, but in this section, is the covariance between the residual, so y minus your prediction, and your original x. So you're saying if you start with your assumption of uncorrelated noise, right? No? Saying if we have the optimal coefficients, I then the prediction error will be uncorrelated with the regressor. So what in plain English, what they're saying is if you predict as well as you can, then whatever is left will not have any relationship with what you can predict. So your X is used to predict things. Your residuals are what remains after the predictions are made. So you're saying you're predicting to the best of your abilities, and what is left is just actual noise. So that's not correlated with your data, because that is an assumption you make that your noise is uncorrelated with your data. We'll get to that later. There's a whole chapter about that. But because of that, your leftover correlation, the correlation of your residuals with your data should be zero. Moreover, expected prediction error over all x should be zero. So you should be able to, on average, get your predictions right. Because again of this assumption of zero mean noise that you made. And he's not very clear about that here, but it is important to remember that. At the same time, just remember that per point that is not zero. So this expectation is very important. The expectation means over the entire data set. Per point, your error might not be zero, but over the entire data set, on average, your error will be zero. So yeah, conditional expectation not zero. Similarly, conditional variance is not zero. So condition on fixing this for a particular point, it's not zero, but over all of the data set, it for the variance, again, it depends on the noise variance assumption that you made. Hopefully this section was clear, because this was important. If not, stop me. Okay, estimating the optimal linear predictor. Okay, I've already gone over 1 hour. Wonderful. I need to practice teaching faster. Yeah, I can move a bit faster for sure. You guys are smart people. Okay, to actually estimate this beta from the data, we need to make some probabilistic assumptions about where the data comes from. One of these assumptions is IID, and I've hopped on this for a while in the first chapter, so I'm not going to IID again. If it is IID with unchanging covariances, so the noise covariance is with unchanging covariances. I see. So the data set. And then if we look at the sample covariance, they will converge on the true covariances. So you are saying if you give me enough samples, so if this is my distribution, if you just give me 2 samples, I probably won't be able to estimate it well. But if you give me multiple samples, then I probably will be able to tell you the exact value. So the sample covariance will converge on the true covariance. That is sort of what they're saying. We will look at unbiasedness at a later point, but right now this is it. Yeah, yeah, that is all they're saying. So we go back to this closed form solution that we have from chapter 1, x transpose x inverse x transpose y. This is your estimate. So typically when he adds a hat, he means it's an estimate, and this is the true value. So the estimate converges to the true value as we get more and more and more data. On the other hand, another way of fitting this beta is to start with the in sample mean squared error. So yi minus xi times beta. So per point, calculate the squared residuals per point. That's what you're doing, right? This is the residuals. So you'll find this term used a lot, like sum of square, residual sum of squares, and that's what this means essentially. So the mean squared error is 1 by n times sum of residual squared. Um, and we can do this and minimize it, and eventually we we get some sort of estimate, but it doesn't tell us anything about the convergence of beta. So you can get this and you can fit a beta hat, but that doesn't tell you about how this will work as you get more and more samples. Here you can do that because you're working with a closed form solution, and you have the matrix, and you know what you know that 1 by n x transpose, or x transpose x to be more precise. That's what he used here, right? Or did he use? Yeah. It depends on how you define x, but anyway, because we know this, we can say that this will converge to the true value, but here we have nothing of the sort. And so it's hard to say anything about convergence, but you get the idea of like the importance of different kinds of estimators and the risk for the estimate. Okay, unbiasedness and variance of ordinary least squares estimates. Um, Ordinary least squares is often referred to as OLS, just for those who don't know. Um, the key fact that beta hat is linear in the observed responses. We can use this by writing as you used to from your linear regression class. Not very important. This point we got at before, this expectation being 0 and correlation being 0. This was an assumption you made on the noise. You said noise is 0 mean, and you said noise is uncorrelated with the data set. Okay. Anyway, I would very much encourage you to go through the math. I typically add notes for all the math, so it should be straightforward to read it. But the idea is just that there is no bias. So the expected value of your estimator converges on the true value. That is what they're analyzing here. And because it converges, there is no fixed amount that it differs by. That's called an unbiased estimate. So in terms of a graph, if this is a true graph, then you are saying, as I get more and more data from this, my estimate for the red one will go and converge on the true value of the orange one. For some estimators, what might happen is your red one might actually go and stay around here, which is like a fixed distance away from this orange one. So no matter how much data you throw at it, just because this estimator is constructed that way, it has a term called bias that it differs by. And yeah, that's all I want to say. He also analyzes the variance matrix that I don't really want to get into here. I did give you a bunch of notes about this, and you can ask me more questions about it later. Yeah. If anyone has a question about this right now, then I can get into it. Let me know. Okay, in the interest of time, we will move forward. Oh, it's not 9:40. Why does it always show 9:41 a.m. on my iPad? It's 9:27. This is so weird. Wow. Oh, okay, so we are on time. Okay, that's not bad. I have 14 minutes to complete. Oh, it's actually pretty good. Okay. Um, okay, so he uses this law of total variance to analyze the variance of the estimator. So this is super important. The law of total variance, and look this up on Wikipedia, is this thing that the expect the total variance is the expectation of some variance versus I don't remember the exact statement actually. Just look it up on Wikipedia. But it deconstructs the variance of this estimator into two terms. So the expectation of the conditional variance plus the variance of the conditional expectation. Correct. So that's how it decomposes this. And we have seen iterated expectation in the last chapter before, by which I mean um, expectation of y given x is actually the expectation of y. This is the point this is what we mean by iterated expectations. And we also had a proof for this, so definitely look it up, try to prove it yourself. And by proving it for yourself, I just mean it gives you familiarity with the terminology, that's all. Huh. Okay, so we obtain an equation for the variance of your estimate in terms of the data, and it's proportional to 1 by n, which means that it will this turns to v, right? So it should reduce, right? Yep. Sigma square by n, points 1 to 3 still hold. Yep, fair enough. This converges to the true variance. And so the estimator is a function of the noise and the amount of data that you have, which is fair. The more the data, the better your estimate, and the less the variance of the noise, the better your estimate. I hope that is clear from this equation. The internal term converges, and then what's left is how much is your noise varying and how much data do you have. That's all that they're trying to say here. Okay, moving on. Three very important factors: shifting distributions, omitted variables, and transformations. And that is basically the rest of the chapter. I will try to move a bit faster. So what he is saying is that the best beta, or the perfect the best explanation of the data in the linear model will depend on the distribution of the regressors unless the conditional mean is exactly linear, which means if you have a flat function, then you don't need more than two data points to describe it. But if you have some random function, then two data points are not enough, and you need like more data points to describe exactly how the function varies. That's one thing. And by linear, I mean like any linear model like can be described by 2 points exactly. Anyway, this is if the true conditional mean is like the best possible guess you can make, right? That was the idea. So it will depend on the x's that you get. That's what he's trying to say. And the basic point of this example that he gives you next is by drawing some data set from some distribution, then some other data set from a second distribution, and some third data set from a third distribution. So you know that the true distributions that they are drawn from, you sort of know in your head what you should expect. And what you find is that a linear model that is fitted through all of this data explains 96% of the total variance. And before I get to what this means, you should understand what this means, this 96%, like explaining total variance. What you're saying is, um, if I have a batch of apples, and some apples are good apples, some apples are bad apples, and I want to know how good can an apple be, how bad can an apple be. I can explain like 96% of this whole ratio of from good to bad using this one model, this stupid simple model. Oh, I should just say linear regression. Even though this actual distribution is pretty complicated, this is drawn from some different distribution, this is drawn from some different distribution, this is drawn from a different distribution, which are all more complicated than this linear model. And still the linear model can explain 96% of it. So the point he's trying to get at is, don't try to assume that, oh, because it explains everything, the true model must be linear. Because here clearly the true model is not linear, and a linear regression still explains all of the variance. So in your head, you should think of variance as like the extent to which data is like varying far away from the mean. It's, to be extremely precise, that a standard deviation. But yeah, you can think about variance in that sense, qualitatively. So don't misjudge this 96% explained variance with true model being linear or your assumptions being correct. Therefore, that's it. That's the purpose of that section. Some He gives us some idea about omitted variables. So um, typically when we collect, and this is about like collecting these x's to predict these y's, we may have some z's that may also influence y. And so he gives us this example of like even changing this z, even though z affects y very little, 0.01, right, is this relationship from z to y, and this x to y is 0.99. Even though this might be the case, varying z by a little bit, it's called perturb z, causes some significant changes here and here. So sorry, not here, causes some significant changes in your linear model. I think that was the point, right? To have some non-redundant information distribution, x given z changes, and then the outcome prediction should y change too. Stiff correlation, the size will change the marginal distribution for the other lines and it is different. Trying to indicate how this z is also increases y. The difference is due to changing the correlation between x and z, not how x and z themselves relate to y. Get beat has 0.991, 0.981. Turn to the omitted variables. Okay, so I guess I'm just going to say like this. There is a bit of involved conditional independent stuff that I don't think I have the time to go into right now. So, well, when we get to causal inference, we'll see all of this in great detail. Yeah, you'd also benefit from an introduction to sort of deseparation in graphs. But anyway, I guess the takeaway from this section, forget about this idea. The takeaway from this section is just that the data has some internal relationships, and you might not measure some factors that actually affect your data. And so changing the relationships changes the model by a lot. That was the sum total of this section, at least to the extent that I understand. And maybe one more line about that, like changing those things does not visibly change the data. So visibly there's very little change. It's similar to this setup where so if you think about changing your image pixels by a little bit, your image completely is not going to change. In fact, it will look almost exactly the same to you. But for the model, that makes a huge difference. And that's how that happens. So I guess the point now, the section is about like, where does the model fail and what should you not do with the model. Um, Another point he mentions is that there are actually errors in the variables that we measure. So there might be some true variable u which we want to measure, but we can only measure x. So in earlier times, you didn't have all of these sensors that could take measurements of the temperature at like different levels in the atmosphere. So they had to make do with what they had, go up to a very high mountain and like take measurements there, and then try to think about how this ground compares with mountain, so how mountain could compare with something else, and so on and so forth. So some crude ways of making measurements that we have, but we cannot actually measure the true variables. So and that's just something that exists. Like we can't do that, and we have to make do with what we have. um
Swapnil, one doubt, if time warrants it. So the the error in variables, as Shalizi says that it's eta, right? So
mhm.
doesn't epsilon count for this? Because when we say we are assuming some error, so doesn't epsilon have so doesn't it consider all the errors that we make while getting the data?
That's an excellent question, and to the way I understand this is this might actually be correlated with the data.
Okay.
So you're taking per measurement, you might have some error that might actually vary with the data.
Yeah. Okay. Okay.
But when you say noise, you always, well, not always, but in the generic cases, you say, okay, noise is uncorrelated at the expectation zero and fixed variance.
Yeah. Yeah.
So
Okay.
that's just a way I think about it. I mean, I don't know what else it could be. Yeah, I don't think I have anything more to say. So the summary of that section was just this line, that without better data, the relationship of y to this true value u that we want to measure is just one of the unanswerable questions the world is full of. Right, so actually he does get into this. Now, if you're willing to assume that eta is a very well-behaved Gaussian with known variance, then there are solutions to the error in variables problem. So I guess what I said was probably correct, that he doesn't assume anything about eta, because that may as well just be not very well behaved. So not the same assumptions as noise. Okay, cool. Yeah. So it's important that a lot of assumptions that people make in order to solve these problems are not realistic. And it's very hard to tell when you just have these statistical descriptions without examples. So I don't know, that's part of the reason I like examples. They clarify when something works, when it couldn't. And it forces you to think about, okay, but like on paper, this is fine, but in practice, is this really useful to us? Yeah. Transforming variables. Okay. I think one of the last two sections in this chapter. And we are actually doing okay on time. It's just been 1 hour. We have 10 minutes over time, if everyone is okay with that. Okay, I won't wait for opposition. Um, what he's basically saying is it might not be a linear relationship between y and x. Okay, so you might have to transform x into some other variable f of x, or you might have to transform y into some other variable f of y. And the whole section is about why this is more feasible and more of a sane solution than this. It's not super complicated. um, One of the reasons is that you know from subject matter knowledge that you should transform x. Another reason is you made some noise assumption that is going to change if you change this whole function of x. um, What else do you need? Um, yeah, he creates an artificial example where he demonstrates that transforming X is better, but he also says that this is like just an artificial example. Like, so I'm not going to waste time on that. Just generally, it is better to transform X than to transform Y. For reasons that are described in this section, read it in detail to find out. Okay, so summary, how to find the right transforms: either fix the functions in advance and based on guesses about what could be good functions, or fix the function in advance by you always using the same library. So there are a bunch of different functions. X can be transformed to sine X, X can be transformed to cos X, X can be transformed to X plus 2. Whatever that function does, you have some library of function that does this, and then you fit your Y to your X to find the correct parameters for this transformation. Or C, try to find good functions from the data, and this is complicated because now you're searching for the space of functions, and that leads us to some interesting techniques, but we have entire chapters on each of them. Okay, this super important section, he said that typically we add some assumptions, but in this section he actually describes every single assumption. So read this very, very carefully. We have already mentioned most of this throughout the chapter, but what this implies is not clear until you read all of this. So what does the IID assumption mean? It allows us to factorize the joint likelihood of the data, conditioned on the covariates. Um, I shouldn't say joint all the time there, but I, yeah, we had this discussion. Um, I don't think we have discussed maximum likelihood estimates, but to give you a brief introduction to data likelihood. So if you have a certain model, and your model tells you your data is probably described this way, um, then for your data x will lie on this axis. You have certain probabilities. I shouldn't say probabilities, but yeah. Um, and you multiply these together to figure out how likely the data is together. That that is your that is your p of yi given your xi. So if you have these xi's, then these are your yi's, and multiplying them together gives you the likelihood of the data under that model. There is this idea of normalizing constant, but I really don't think it's a good time to get into that. And the way you find the best model is by saying, okay, under which model is this maximum, and that is max likelihood. So it will give you an equation that you differentiate, and you maximize this, differentiate, set it to 0. Then you figure out your parameter values that allow you to say this is the maximum likelihood estimator for this data. I This is actually a very detailed subject, and you could spend an entire lecture on it, but I just glossed over some things. But you should definitely look up maximum likelihood estimation. And okay, so now that you know there is an MLE, why is this MLE good? Well, because there are different ways of estimating data. Some estimators require a lot more data to converge than other estimators. And the MLE is good because this figuring out a likelihood for the data, then maximizing like differentiating that likelihood, setting it to 0, or using some other techniques, because sometimes it's not possible to find closed form solutions. Recall that closed form was when you can solve it by writing an equation for the solution. So it's not possible to find a closed form solution because of certain challenges. In those cases, you can use other techniques, And if anyone is familiar with EM algorithm, that's expectation maximization. That's another way of doing that. Um, and yeah, so yeah, I don't have much else to say about this particular section because it assumes some understanding of likelihoods. So I won't try to go and confuse you, but definitely read up, try to understand it, and we can get back to it after you understood maximum likelihood. Um, yeah, I don't feel like I want to say anything more. Examining the residuals, this is important. So um, we discussed initially that, okay, if you are the best fit, then what's remaining, which is your residual, should not be correlated with data X. So one way to test is to fit the model, find the prediction, and then test the residual for structure. Like if your residuals vary a lot with each X, or very little and then a lot, like there's some difference in structure, that's a problem, because that means you made some wrong assumption, or your model fit is bad, or your data is correlated, which is the wrong model assumption. um, Data is correlated with the errors. Yeah, I don't think I want to say anything more about that. So this is an important point, is homoscedasticity, because in the beginning you made the assumption that the error come from this Gaussian 0-1 distribution. Variance normal 0-1. This is called the standard normal, or white noise. So white noise implies three things: Gaussianity, homoscedasticity, and lack of correlation. Homoscedasticity is this idea that each point of noise is drawn from this distribution with a fixed variance. And this is a bad way of denoting variance, but like very hand wavy, but still. So the variance is fixed, so it does not change. So suddenly you're not going to have noise drawn from this distribution. That's the idea of homoscedasticity. Okay. And we have an entire chapter literally titled heteroscedasticity. So it is clearly an assumption that might fail, and yeah, you have to deal with that. How am I doing on time? I'm 9 minutes over time, 8 minutes over time. Okay, 2-3 more minutes and we're done. Significance testing is again a super important section, and if you do not know what hypothesis testing and p-values are, then you should read about it. It is very crucial, especially in data science these days. Hypothesis testing is this idea of figuring out if a change is just by chance or by fluke, or it indicates an actual effect. So if I give you chocolate and your teeth gets like cavities, is it because of the chocolate or is it just by fluke? And I can do that. One way of doing that is by giving you lots of chocolates, but then your teeth might be genetically inclined to be bad and the chocolates don't actually affect that. And so like you have to do a significant amount of testing. I use significant, but that's shouldn't have used that word. You have to do a considerable amount of testing in a principled manner to evaluate this effect. So you have a control group, you have a testing group. So, and these all have to be random people. You can't just take, for instance, you can't take people who go to dentist offices because they might already have bad teeth. So you can't do the survey on those people. So that's what I mean. It's hypothesis testing is this general framework of doing this, except now in the data regime, where it's not as easy to tell things apart. So there is a null hypothesis, there is an alternate hypothesis. So there is a null would be like, this had no effect on your teeth, and your alternate is eating chocolate did spoil my teeth. And then you want to figure out under this null hypothesis, so if there was no effect, then it's still a probability. So even if there was no effect, your teeth were still somewhat likely to be spoiled, right? And that might be because of any other reason except for chocolate. And if that probability is super low, like my teeth could not have been spoiled by anything, like everything is perfect except for chocolate, and then my teeth still get spoiled because of chocolate, then it's probably true that teeth get spoiled by chocolate. And I spoke a lot, I spoke very fast, so let me know if you're confused about what I said, but I will repeat nevertheless. There is a null hypothesis, which means my teeth will not get spoiled by chocolate. There is an alternate, which is my teeth will get spoiled by chocolate. There is an experiment, give me chocolate. Um, and under the null, it is very unlikely that my teeth will get spoiled. There is still a probability, but a very low probability, because everything in this world is probabilistic. There is a chance I might die. Very, very low chance sitting at home in my chair, but there is a chance. So there is a chance that my teeth will get spoiled. Very, very low chance, but there is a chance. And after eating chocolate, if my teeth still get spoiled, then that probably means that that is not just by chance, but because of that chocolate. So that is your hypothesis testing, and your p-value tells you about this chance. So if your p-value is very, very, very low, then that means like, yes, like there was a very low chance and that still happened. So that's what you look for. You set these levels called significant levels. I forget the term now. Um, but that's yeah, that's hypothesis testing in a nutshell. So what we are trying to do is we are trying to figure out if this coefficient is significant. So slightly same sort of significant, but like significant in predicting the outcome. And the important point that he harps on is we cannot test any coefficient individually. It is always, is this significant given the other data that you're using? So what he's saying is you're using a data set to predict a y. You're not just using one data. So that significance cannot be interpreted standalone. So that significant is given the rest of the data, this adds some more value or this doesn't add more value. And he really like shouts at people who like don't do this, who try to interpret us, oh, this column is definitely important for the data. No, this column is important to predict the data given the rest of the columns. And that's it, that's the point of this section. Yeah, so statistical significance, to summarize this, is about what signals can be picked out clearly from the background noise and not just independently what signals can be picked out from the data. From picked out, that's it. So yeah, linear regression is not the philosopher's stone. So again, some warnings that he gives us: don't interpret things this way. So just because a variable has a significant regression coefficient, it does not mean it must influence the response. Just because it has an insignificant regression coefficient, it does not mean that it doesn't influence the response. So yeah, all of this is wrong, and at best can only be right under particular circumstances. So okay, so what if there are no nonlinearities, if there are no omitted influential variables, if the noise terms are always independent of the predictor variables, then are we good? And the root says no, we are still not good. There is no reason whatsoever to suppose that if we change the okay, it describes the distribution. So there's a trying to describe the joint distribution x and y, we have the marginal distribution of x. We sort of change this conditional expectation y given x. And so like he's basically saying like if you move around one particular section, there is no reason that this and this is fixed, there is no reason that the third one should, again, like forget the details. The essential idea is like you're layering assumptions on top of assumptions on top of assumptions. Even if like a small piece breaks, the whole house of cards comes falling down on you. So don't jump to interpreting any of this more than what it is. It is just correlation, it is just prediction. There is no reason to go more than that. And he gives a nice example, not really complicated to understand, so I'm going to skip over that, and I'm going to end at about 14 minutes over time. Okay, questions?
Hello.
Let me stop recording. Is there a question?
Am I audible?
Yeah,
Hello.
yeah.
Actually, I had a question regarding transformations.
Okay.
So whenever we have multivariate data and we apply transformations on that, so wouldn't that disturb the interactions between two variables of data?
You have multivariate data and you apply transformations to that.
Yeah, would that have any effect if the data is supposedly interacting with each other? Like I
That's a good question. And what I would say is the transformations you apply are bijective. So it's one to one. So one point in the original data set is mapped to one point in the new sort of transformed variable. So you wouldn't be disturbing those relationships. Um, they would still hold, is my understanding. And I will tell you why, because correlation is standardized covariance. So as long as the standardization still exists, you should be able to, yeah, you should be able to do the same thing. Those interaction terms should remain the same. Yeah.
all right. Thank you.
Even I had a doubt about transformation. Hello.
Yeah, I can't hear who's speaking. Hello? Josh. Yeah, okay. Maybe my volume is low. Not your fault. Yeah, go ahead.
Yeah, so here in transformations, he takes an example and then shows that why X transformation is better than Y. So, how will we know like when to use Y transformation? That is, he gives three reasons for this. Like,
So your question
so
then
if
is
those
how will
three
you know when to
reasons,
use Y transform?
yeah, so if those three conditions are not satisfied, then can we say that Y transformation is better than X in that case?
So I think the point is he's saying if those conditions are satisfied, X transform is definitely better than Y. Otherwise, we do not know.
Okay,
And he
but
says
then
the
one of the condition,
go ahead. Sorry.
one of the condition is noise, right? So if we transform, the noise gets transformed, and then we don't know the transformed distribution of noise. So we cannot use the Y transformation. So can you give an example where we can use where after transforming we know the distribution of noise as well?
I missed the last part. Can you give an example where after transforming we know that
Like the where if there is a noise it won't matter and you can still do the Y transformation.
where there is a noise it won't matter and we can still. So um, I think the reason that is hard, let me first describe that, is because you want to find your Y's relationship with X, not necessarily Fx, right? Um, because like one of the reasons you do linear regression is so that you can say something about the relationship between X and Y. And if you do this, you have to like inverse transform the distribution of the noise back to the distribution it had when it was added to X as opposed to f of X. And that inverse transform is hard to do. And again, like the example you're asking me to come up with is, let me think about this. So again, can you repeat the question to help me understand better? So you want an example where Y could be transformed as opposed to X, that I follow. Is there anything else?
No, just this, where we can transform y.
I think that's a good question. I don't have an answer off the top of my head, but I'll think about it and post back on the group.
Yeah, because in the exercise section, the last sum,
Mhm.
uh, there is a transformation where first 2 points don't hold. So only the third point in which we add some errors, like uh, we choose to transform x because then we don't know the distribution after transforming the whole thing because of the errors. So I was not sure when we can use the y transformation.
Okay, so this is about the last question in the exercise. That's what you said.
Yeah.
Which kind of transformation is superior for the model where y given x is drawn from normal root x, comma 1? Hmm. Okay, I'll think about this and get back to you.
Okay.
Thank
Thank
you.
you.
All right, stop recording.